Alright guys, welcome to another episode of Cuda Education. Today we are going to talk about semaphores. Now, before I get into that, remember guys, if you want to join in the fun, if you want to practice the Vulkan API and have code running on your Windows-based machine with a Vulkan-capable GPU, check out tutorial number 1 and tutorial number 13. Tutorial number 1 is to install the Vulkan API itself. Tutorial number 13 is to install the examples that are freely available on the internet. The example that I'm running with now to go through specific topics is computecloth.cpp, and you could just Google that, computecloth.cpp, and you will see the raw code and everything that sort of I use to have running code on my machine, and then go through some examples of specific topics. So we're dealing with semaphores. Now, if you guys remember, semaphores are it's a synchronization thing on the GPU. So it's dealing with synchronization. Remember, generally speaking, when you're dealing with the GPU, you are talking about parallel processes. So you're doing many things at the same time. And in order to have some level of organization and consistency, you have to make sure that you have some kind of synchronization. So the first order of business is I'm going to just go through a brief review of fences and semaphores. Okay, so you guys remember I discussed fences and semaphores in a previous video in the Vulkan API discussion series. So this is just a quick recap, but I'm gonna go fast because I already went into depth before. So on your machine you have CPU, right, which is your central processing unit, usually by Intel or some other manufacturer that does CPU. And then you have your GPU. GPU might be your NVIDIA graphics card. It might be the AMD has graphics cards or whatever. Remember, GPUs generally are parallel processing stuff. So that's where all your graphics and parallel processing work gets done. So let's just quickly go through fences. Fences are CPU to GPU synchronization. So you might submit a call to the GPU, and then you wait and then once the process is done, the GPU signals back to the CPU that it's complete. So this process is called a fence. So this is maybe I'll do it down here. This is a fence. Okay, this is a fence. It's synchronization between the CPU and GPU. You submit something to the GPU, you wait, and you submit, and then you signal back to the CPU that it's done. It could also go in reverse. The GPU maybe could do something on the CPU and then signals, and then it waits, and then it signals back to the GPU that it's done. But this is the domain. Anytime you see fence, it's CPU to GPU synchronization. And if you don't use a fence, you get other issues. So let's say you're submitting commands to the GPU. If you don't use a fence, you're just gonna keep submitting commands, right? And maybe after a length of time, maybe like a couple seconds or a minute or so, only one process is completed, but you're still submitting stuff to the GPU. So a fence is used to make sure that all of this stuff doesn't happen, that you submit something to the GPU, right? You wait, and then once it's done, you signal back to the CPU that it's done and what have you. So that's fence, okay? But that's not the topic of our conversation today. Today, what we're going to talk about is semaphores, okay? So again, like in the previous video, just going to recap really quickly. Okay, so we have CPU and GPU. Semaphores is GPU to GPU synchronization. So you have, let's say, process 1, right? And then you have process 2. Now you want to enforce that before process 2 starts, process 1 is finished. So you have process 1, and then you have process 2. Process 1, then process 2. So this synchronization restriction, or this synchronization rule is in the domain of semaphores. Okay, so this where you have a process on the GPU and you have another process on the GPU, and you're trying to enforce a relationship between the two processes, that is distinctly considered a semaphore. Okay, and that's the topic of conversation for today. We're dealing with semaphores. We're dealing with GPU related synchronization, nothing to do with the CPU. So basically, when I'm discussing semaphores, I don't discuss the CPU. This is GPU related stuff. Process 1, process 2, you enforce this. Process 1 has to be done before you could do process 2. That's the world of semaphores. And that's the big overview. Again, I go through it in more in depth in a previous video. The thing is that, from what I understood when I researched this stuff, fences, usually you have more flexibility with fences. You could query the state of fences. You could do like a lot of other stuff. I don't know if things have changed with the updated spec, but with semaphores, you kind of just have these rules. You submit the rules, the semaphores, and you just take it as a given that it's done. You don't always have necessarily, you can't always query the status of semaphores. I don't know if it has changed or if things have changed, but with semaphores, there's a little less flexibility. It's all on the GPU, and you just submit the rule, and you could basically assume that it's a given that those rules are enforced. You're not going to do process 2 until process 1 is done, etc., etc. So now we're going to get into compute cloth. Now the thing is that, again, what compute cloth is you have a ball in the center of the stage, right? So you have this ball, and then you have a cloth, right? And this is and it says Vulkan on it, and the cloth descends down onto the ball. So when it descends down onto the ball, the cloth, like it's wrinkled all over the ball. So this is the ball, and then the cloth wraps around it, right? So my drawing isn't good, but basically you have gravity carrying the ball down. I mean the cloth down onto the ball, and then the cloth wraps around the ball, sort of, right? So that's the algorithm that we're working with. I've discussed it in previous videos, and we're just continuing this discussion. But again, what we're going to focus on is semaphores this time. So in the compute cloth process, there are a couple of things that we have to do. I'll just maybe put a little thing up here, and then we'll have the ball here, and it's descending down on it, right? So that's a cloth. This is our sphere or ball, and it's descending down on it, okay? So there are two major things that we have to do with this algorithm. This is semaphore related stuff, so it's two processes on the GPU. But we have to manage the order in which we do it, and we have to enforce specific rules about the the order of things, how one thing gets done before the other. So the first major thing that we have to worry about is compute commands /work. Okay, so you're not going to you have to compute this stuff. So the cloth, you have the cloth, and then you have the sphere or the ball, and you have to compute, for example, the cloth moving lower and lower because of gravity onto the ball. Then once it hits the ball, you have to compute how the cloth changes because it's now wrapping around the ball, right? And there's also an option to simulate wind. So you could press a button and you'd simulate wind. So the cloth is over the ball, and then wind is like making it wavy through with the wind, right? So there's compute commands /work that we have to do. And then number two, there is graphics commands. /work. Okay, so now graphics commands is, so you computationally calculate how the pixels are going to change, how the cloth is going to wrap around the ball, all of that stuff, gravity, all of that stuff, wind, all of that stuff. But then graphically, you're going to have to display this stuff. So you have to display the fact that there is a cloth. You have to display the fact that the cloth has texture on it, and it has lettering on it. It has an image on it. It has the Vulkan logo on the cloth. Then you have to render and have the ball there, and the ball is a black color, right? And obviously, you have to render as the cloth goes down on the ball, how the cloth changes as it hits the ball. Okay. So with the graphics side of the equation, there are two sub-processes that you have to worry about. You need to worry about render work, and you have to worry about presentation work. Okay? So I'll get into this, I'll erase this and get into it in more detail. But you have to remember, and I even forgot this when I was initially investigating it, is that you have to create the image, draw the image, color the image, map out the vertices of the image. Maybe you have lines that connect the vertices of the image, color the inside of the image, all of that stuff. So you have a ball, maybe it has vertices, well, maybe not, but you have a ball, and then you have the color inside of the ball, and then you have a cloth, maybe you have 4 vertices, and then you connect it, and then you have a texture over it and all that stuff. So you have to render the image, okay? You have to actually create the image, right, in the system. You use vertices, you use color, you use texture, you use all kind of stuff, right? So you have to create the image. This is independent of everything. You have to create the cloth, you have to create the sphere. That's one thing. Then you also have to present it to the screen, right? So you're presenting now the image that you're created to your computer monitor, right? That's what allows your eyes to see what's happening in your application, right? You actually have to present it to the screen. But these are two distinct processes that you have to account for, and you have to manage it, because you don't want to be rendering an image while you're also presenting it to the screen, right? That doesn't make sense. You're actively drawing the image, and you're going to present it on your computer screen. You're going to have an incomplete image, or undefined behavior or whatever. Same thing. You're not going to present something to the screen if you're actively drawing it. Okay? So you're not going to present an image to your computer monitor if you haven't finished drawing it. Makes sense, right? So with the graphics side of the equation, it's a little bit more involved because you have render work and presentation work, and you have to manage your relationship with these two. You also have to manage your relationship between compute related stuff and graphics related stuff. So you're not going to do graphics work if you haven't fully finished computing, you know, what graphics you're going to show, right? And remember, the compute stuff is the gravity, it's how the cloth is going to change as it hits the ball, all that stuff. And then the graphics stuff is, you know, creating the images and presenting it to the computer monitor, presenting it to the screen. I don't know what you guys have, 4K monitors now and all kind of stuff. You know, my knowledge only goes up to 1080p, but I guess that's old news now. But anyway, so we have to manage these things. Again, all of these things is GPU related stuff, okay? So we have to manage these relationships. Another thing that we're gonna have to take into consideration, I was gonna erase everything, but maybe I'll just leave it here. All right. So another thing we're gonna have to consider is semaphore flags. Okay. All right, so I'm gonna go this way because maybe the screen you guys not gonna see. So the first thing that you're gonna have to do, okay, yeah, we got room over here. Okay, so the first thing you're gonna have to do, let's call this number 1. So you're gonna have to wait for a process to be done before executing your process. Okay? And as part of this, the important thing is wait, right? As part of this, you're going to have to specify what stage of the pipeline needs to wait. All right, you guys able to see all that, right? So wait for a process to be done before executing your process. Specify what stage of the pipeline needs to wait, okay? So remember, we're dealing with parallel processing. We're dealing with, we're trying to make things fast. We're trying to do things as fast as we can, because remember, we don't want our frame rate to suffer. We don't want things to be slow. So you have to wait for other things to be done before you could do your thing. So just like how when we had the initial piece, we talked about process 1 and process 2. So in this case, you're waiting for process 1 to be completed before you start process 2. The thing about it is that the synchronization is granular enough and is specific enough where you're not going to have the whole pipeline wait, or you're not going to have all things related to the pipeline wait. You're only going to wait when it relates to things that are like will affect your process number 2, or things that will affect what immediately you're dealing with. This is a good thing because you don't want to halt all work on your pipeline just because of something that only needs, you know, specific synchronization. This is the battle of parallel processing and computer graphics and stuff, is that you could do too much synchronization where you're holding up your whole application, you're holding up everything. And while it's good to hold up stuff and have complete synchronization and stuff, the bad part about it is that you're slowing down your application. Your frame rates are gonna drop, right? So you wanna specify what stage of the pipeline needs to wait. I'm not gonna talk too much about it more here. When in the next video, when we actually dive into code, I will talk about it a little more. But the first thing you have to do is wait for a process to be done before executing your process, and then specify what stage of the pipeline needs to wait. I still need to do some work on this piece, but just understand that you have to wait, and you can specify what stage of the pipeline you're waiting on or needs to wait for this specific synchronization, right? And then number two now is signal that your process is complete. So signal that your process is complete. So after you've waited for the previous process to execute, let's say process number 1, and then now you're doing work on process number 2, you need a way to signal that your process is complete, right? So you're basically telling your application, okay, process number 2 is done, it's finalized. I have a flag that says it's done, it's finalized, and you could move on to the next iteration or move on to the next thing that you need to do. So maybe if you had process 1, process 2, and process 3, you signal that process 2 is done, and then you move on to process 3, right? Same thing with here, for the process 1, you're waiting for it to be done, but you need a way to communicate to the application that process 1 is done, and now you could start process 2. So that is the semaphore flags, I like to call them. Maybe they have a more special name for it. Real quick, I don't want to confuse you at the risk of confusing you, but the two stages that we work with in ComputeCloth.cpp is VK pipeline compute shader bit. Okay, so VK pipeline compute shader bit and VK pipeline stage vertex input bit. Okay, but we're not gonna, when I get into code, we'll discuss that more. But there you have it, guys. You have your semaphore, compute work, graphics work. In the graphics, you have render work and you have presentation work. This is our application over here, tutorial number 1 and tutorial number 13. If you want to get this stuff running on your machine and follow through with live code running on your machine so you can learn the Vulkan API, you have to wait for the previous process to execute, and you can specify what stage of the pipeline, and these are the things that we use to specify the stage, and then signal that your process is complete. Okay? All right, there's more things that we have to discuss before I create the next video where we're jumping into code. So let me, I'm gonna erase all of this because I need this space. So you guys see this now. So let's just move quickly because this video is already long and I don't want to lose you guys. Okay. So the next thing that we have to tackle is that remember we talked about render work and presentation work. Okay, so in a previous video I also discussed the swap chain, right? And I was like, why is it there is this render complete flag and there's this present complete flag? And I'm like, why do we have to worry about render complete and present complete? But then I remembered my previous video where I discussed the swap chain, and I'll rehash that conversation here really quickly. So remember now, in the previous video, we had a swap chain, right? And a swap chain is a series of images. Oh, I'm gonna get in trouble now. Is swap chain one word or two words? I don't know. I know you guys are gonna beat me up about it, but okay. So you have a swap chain, right? And then you have presentation, right? Okay, so you have your swap chain, which is a series of images that you're building to submit to presentation. Now, presentation, basically, what presentation is, it's your lovely, expensive computer monitor, right? Of like, let's say, I mean, I'm not going to use this because it's too, but let's say it's a triangle, okay? So presentation is what your eyeballs see, right? So this is your computer monitor. Let's say it's 4K, you know, computer monitor, right? So computer, this is your computer monitor, right? And you're presenting what you've rendered to the screen, okay? So this is your monitor, right? And you're presenting it to the screen. But remember I said there is render work and there's presentation work, okay? Under the graphics commands / work, right? So graphics, this is graphics related stuff now, right? So, I mean, really it's, you're presenting this, but I'm just using a triangle. So remember now, the swap chain, you're loading up the swap chain with all these different images. Each image represents like a frame. So you're loading it up with like these triangles, right? I use triangles because that's what I did in my previous video, right? And all these triangles have color in them, right? Obviously, for compute cloth, it's not triangles, it's actually this thing here, but for simplicity, I'm just using triangles, right? So you're loading up the swap chain with all of these images. There is render work and there is presentation work. But render work, really, you actually have to do stuff to make these images. So you're gonna have vertices, right? You're gonna have lines connecting the vertices, right? And then you're gonna have color, okay? So again, you have vertices. Let's do it again. Render work, right? Render work, right? So you're actively drawing this stuff, right? So you're drawing this stuff, right? You have the vertices, you have lines connecting the vertices, and then you color it. This is what you call render work, right? So you're not gonna be doing render work and presenting to the screen at the same time. You have to render first and then present. You know, all this stuff eventually gets to the screen. So this kind of affects your FPS, frames per second, and all that, because you're loading up the swap chain with you know, these images. You're doing the rendering, you're loading it up, and then you're presenting to the screen one by one frame at a time, right? Obviously it's not triangles, it's this stuff right here, but you understand what I'm getting at. So that's why this one was called render complete. And this was called present complete. Okay, so we will when we go into code in the next video, we will discuss this stuff. But this is you know, this is an important piece of the puzzle that you have to understand, that rendering is complete, you have drawn the image, and presentation is complete, you have shown the image on your computer monitor, okay? So just keep that in mind. The last thing that I want to discuss, I'm gonna have to do a little erasing again, but just bear with me. The last thing I want to discuss is the idea of first draw. Okay, so in the algorithm, in the application, there is a distinction between the very first draw that you make and every other draw after that, right? And you're basically you're constantly calling the draw function. Okay, you're constantly calling the draw function, but you're constantly calling the draw function, but the thing is that you want to, I'll use a different color just because, you know, to change things up. All right, so you're constantly calling the draw function, right? So the draw function is, you know, what you're using to actually draw stuff and all that, okay? But there is first draw, versus not first draw. Okay? So with first draw, it's the first time you're calling the draw function. Okay? Initially when you start up the application and everything, the first draw variable, let's use a different. So first draw is set to true, right? Over here. Okay? First draw is set to true. Let's just okay, first draw is set to true. So when you're drawing for the first time, you don't care about synchronization or anything because it's the first time you're doing anything. So you could kind of be a little reckless or just freelance or whatever because it's the first time you're doing anything. No other process is happening before. So you could kind of skip maybe worrying about process one or the previous process because it's the first time you're drawing. However, when you're doing after the first draw, now you have to worry about previous processes. So because you have to worry about previous processes after the first draw, you have to set first draw. You have to set first draw. You have to set first draw equal false. And that makes sense because you have previous processes that are being executed. So now you have to accommodate for the fact that you have previous things that need to be done before you could proceed with what you want to do next. So that's it, guy. And it's all based on the draw function, right? The draw function is what's drawing everything and making things happen on the screen and all that, right? So you make a distinction between, we initialize the application with first draw being true, but after we do the first draw, we set first draw to false. And for the rest of the application, we pretty much keep first draw as false, okay? But it's an important distinction because you have to synchronize and make sure that your previous processes are not colliding with what you're trying to do now, that the previous processes are done and you could continue with you have to verify that the previous processes are done and you can continue with your work once the previous processes are done. Anyway, guys, that's it for Semaphores on the Compute Cloth application. This is the way I see it. If there are any corrections, I'll make another video correcting stuff. Please feel free to comment on what I've discussed here. If there's anything wrong or anything you disagree with, let me know. But this is an important part of the Vulkan API. parallel processing, you have to do synchronization. You can't do too much synchronization because you will slow down your application to a crawl. You can't do too little synchronization because then things are not organized and lining up properly, and you're miscalculating stuff, or you're showing incomplete artifacts on the screen, incomplete images. Maybe you might run into memory issues, I don't know, all kind of undefined behavior. So synchronization is very important. Semaphores deal with GPU, managing GPU processes and synchronization. Fences is CPU to GPU. You kind of submit the semaphore stuff and you take it as being enforced and done. As far as I know, it might have changed now in 2022, but as far as I know, you have a little less flexibility with semaphores as opposed to fences when it comes to querying the status and maybe, you know, control and doing other stuff. Anyway, guys, remember tutorial number 1, install the Vulkan API on your Windows machine that has a Vulkan capable GPU. Tutorial number 13, you get all of these examples, including computecloth.cpp. It's a series of examples. If your GPU has ray tracing capability, so the RTX cards from NVIDIA, you will also, there are some ray tracing examples. My graphics card is a GeForce 1050 Ti, so I don't have the ray tracing capability just yet. So I'm gonna have to get another card or machine or whatever, so I could get to ray tracing. But before we even get to ray tracing, we gotta cover the basics. Thank you guys for watching. Subscribe to the channel. Tell your friends. Learn something. It's cool to play video games, but you also want to learn something so you can make money and have a career in computer graphics. And there's it's not just video games. It's simulations. It's you know, commerce, retail, all kinds of other applications. And also remember, Vulkan is not just computer graphics. Vulkan is also compute. So you could use your GPU to parallel process and do things really fast, make calculations, do simulations really fast. Vulkan is platform agnostic, so you don't need, you could do it on a GPU, on an NVIDIA GPU, on an AMD GPU. I'm assuming with the new Intel Arc GPUs, you'll be able to do it. And you know, Raspi and Linux and all that stuff. So Vulkan is platform agnostic. It's you know, you could use it on any kind of machine, all that stuff. All right, guys, I think that's it for now. I will have another video that goes into actual code with ComputeCloth, but we needed to discuss this stuff in order to have you know, to benefit from the discussion when we dive into code. All right, have a good day. Bye.